In this video, we'll be taking a look at software, its nature, and the different categories different software applications tend to fall into. We'll also start our exploration of software engineering and discuss the software engineering layers. Since this is an introductory course on software engineering, a good question to start with is, what is software engineering? From the name, we could probably infer that it has something to do with building or designing software. But there is a more standardized definition we could use. But where can we get it from? Well, a good source for anything standards related, especially relating to software engineering, is the Institute of Electrical and Electronics Engineers, also known as the IEEE. The IEEE is a professional association for electronics and related disciplines, which includes computer engineering, software engineering, and computer science. The IEEE is said to produce over 30% of the world's literature in this space, including computer science. And it also is one of the major publishers for many academic journals and conferences in this field. Another large area for the IEEE are standards. And of course, they have a standard that defines what software engineering is. So this standard states that software engineering is an area of computer science which relates to the techniques, methods, practices, and tools for the application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. That is, the application of engineering to software. There is also a second part of this definition, which states that it is also the study of the approaches, as in one, in order to develop high-quality products within a specific budget and time. The key here is the systematic, disciplined, and quantifiable approach. We're not simply jumping into coding and hoping for the best. We're taking a disciplined and methodological approach to building software that is built on best practices that have been proven in the industry over time. Before we can dive more into software engineering methods and practices, we need to have a better idea of what software is. Being computer science or engineering students, you are of course familiar with software as computer programs made up of lines of instructions or code. However, software is much more than this. It's also the data structures that enable programs to manipulate and store information, as well as the documentation that describes the operation and use of those programs. This last definition in particular will be an important focus of this course. This documentation is not just end-user documentation, such as the user manual, but all of those work products that go into the development of the software system, including requirements modeling and design work. These can be in the form of written text, diagrams, interface mockups, or code that defines ways software can be tested. But what is the nature of software? And how is it different from designing and creating other products, in particular hardware products and physical objects? Well, on the screen right now is the hardware failure curve. This shows the typical failure rate for physical products over time. You can see that there is a high failure rate early in the product's life due to manufacturing and design defects. We call this the infant mortality period. So this would be when you get a product dead on arrival, or fails a relatively short time thereafter. That's after you receive it. So after this initial period with high failure rates, we have a period of relatively low failure rates. This is after initial defects have been repaired and we reach a steady state where the product is functioning correctly. However, as this is a physical product, parts eventually start wearing out. And that means that we start having a higher chance of failure as parts start failing. So we see a rise in the failure rate, and the product eventually is going to require complete replacement. Software, however, is not a physical object. It's not manufactured in the classical sense. It doesn't have physical parts that wear out. Failure for software is often a crash, data loss, or the program failing to run correctly. So what might the failure curve for software look like? You might think that it should look something like this, where we have a high initial failure rate due to bugs and other issues that developers fail to correct before releasing the software. But this failure rate drops as patches and updates are made to the software, until we reach a point where failure is unlikely and things remain relatively stable. Unfortunately, this idealized curve is rarely the case in real life. While it is true that software does not wear out, it does deteriorate over time as a result of change. What we tend to see in real life looks more like this actual curve, where early in life software suffers from defects and bugs that were not caught in development. But over time, developers repair, patch, and update the software, and the failure rate declines, just like we saw before. But what we didn't catch in that earlier curve is that eventually change is needed. Perhaps a new feature is requested by the customer, or new hardware is released that needs to be supported. This change introduces new errors and defects and increases the failure rate. Again, developers slowly correct the issues and the failure rate drops. This cycle of change and then maintenance to correct defects continues until eventually the software must be replaced. But why does it need to be replaced? After all, software doesn't wear out. Well, the cumulative effect of this cycle is an increased failure rate. As more and more changes and new features are added to the system, there's more to maintain and more areas where bugs or defects can occur. Eventually, the system will reach a point where it makes more sense to start over or rewrite large portions of the software from scratch than continuing to make changes in this way. So, with that in mind, we should now discuss the different categories or types of software. What you see here are 7 very broad categories of computer software. These are a generalization, and you'll find software might belong to more than one category, or that there's categories not listed here. But typically applications will fall into one of these 7. So let's go through them one by one. The first is system software. Applications in this category support other programs. So this can be compilers, editors, file management utilities, operating systems, drivers, networking software, or anything that allows another program to be created, run, or in some way function. So one example that you most likely use would be an operating system, such as Linux, Mac OS, or even Windows. These are desktop operating systems that would fall under the category of system software. The next category is application software. Application software encompasses programs that solve a specific business need. This could be things like Word, PowerPoint, and Excel, which are commonly used in business and education. It can also include programs like Photoshop, that's frequently used for creating and editing images. However, it's not limited to just purely business use. It can also be programs that serve a broader need, like providing entertainment, such as video games, or applications end users frequently use, such as a web browser for accessing web pages. The key here is that the application software is standalone, meaning that it's installed locally and most processing is done locally. This category is also sometimes referred to as desktop software. Next is engineering or scientific software. This category includes any number crunching, data science, or technical design programs that might be used in research or industry. There are quite a wide range of applications, from astronomy to computer-aided design to genetic analysis and much more. Much of this software is custom designed for the task, but there are some off-the-shelf solutions for common tasks, such as AutoCAD for computer-aided design and drafting, and there is some overlap here with application software. You could have a program that's both engineering software and application software that runs on a desktop, for example. Our next category is embedded software. This is software you likely use every day, but don't realize it or interact with it directly. Many electronic devices, from something simple like a TV remote to a thermostat to cars, have microcontrollers or even small embedded computers that power them. Shown here is an ATmega 328P microcontroller. This is a fairly common microcontroller used by hobbyists and for prototyping, and it can be found in things like Arduino development kits. These microcontrollers are programmed directly, typically using something like assembly, C or C++, and unlike a modern desktop operating system, they typically run one program at a time that controls hardware by taking and giving output from the pins of the chip. For example, on this TV remote that I showed, when you press a button, some software on the microcontroller turns that into an infrared signal and sends that to the TV. This is controlled by sending a signal to an infrared LED to send a specific signal to the TV. As an end user, we don't really interact with that software directly, but it is embedded into the remote, and it does power that operation. So some other examples might be things like keypad controls for a microwave, digital functions of your car, drones and RC cars, and likely most electronic devices you use have some sort of microcontroller embedded in them that has software on it. The next category is product line software. What sets this category apart is the use of reusable components, assets, and designs to create a range of similar products. One example that you've likely used before is Microsoft Office. Microsoft Office is a collection of applications including Word, Excel, PowerPoint, and others that provide a range of different functions. But the key here is that they reuse components and designs in each application. This has several advantages for the developer. Using software assets speeds development and reduces maintenance, helping to lower the costs and create new applications more quickly. For end users, this also helps to provide a standard interface and designs which lowers the learning curve when you're using new software in the same product line. If you've used something like Microsoft Word, you're probably familiar with those same icons and that same ribbon at the top that something like PowerPoint or Microsoft Excel uses. Another example would be something like Adobe Creative Cloud, which includes programs such as Photoshop, Acrobat Reader, Premiere Pro, as well as many others. Autodesk also provides a line of products in their Architecture, Engineering, and Construction collection. Next up is web and mobile applications. Our textbook combines these into one category. However, there are some important distinctions between web and mobile applications. Web applications are offered as a service through your web browser rather than being installed locally, and they typically store any data remotely or on the cloud. For example, Office 365 is now offered as both a web application that you can use without installing it via your web browser, or as a local desktop application. Office 365 also offers stuff like OneDrive to allow you to store those files remotely. Sites like OWL, our learning management system, or YouTube can also be considered web applications. These applications typically work on a service model, either requiring a recurring charge or being ad-supported. Mobile applications are what you would expect. Applications that are designed for and run on mobile devices, such as smartphones or tablets. This type of software typically has unique design considerations and constraints, such as the support of touch controls, more significant hardware constraints, limited screen resolutions, and more significant access control restrictions. There are many possible examples, such as TikTok, Snapchat, Instagram, and many others. They can range from social media clients to mobile games to productivity software, such as mobile versions of Outlook and Microsoft Word. The key here is that they are designed for and built for mobile operating systems, and they run on mobile devices like your smartphone or tablet. The last category we'll look at is artificial intelligence software. This is a rapidly changing area, but a common trait of these applications are making use of heuristics to solve complex problems that we typically could not solve using straightforward computational solutions. Rather than programmers creating rigid rules and code, artificial intelligence software is typically created by training models on massive sets of examples. For example, if we're creating software to detect spam emails, we might train the model with a large data set of examples of emails that are labeled as spam or not spam. The goal being that the model would learn specific features in the data that would allow it to classify new emails it hasn't seen before as spam or not spam. Traditionally, a common use of AI software like this was this kind of classification. However, a rapidly growing use case is generative models that create new outputs based on examples rather than a simple classification. One example would be large language models, such as ChatGPT, Copilot, and Gemini. These are used for natural language processing tasks and creating text-based outputs. For software engineering, these applications pose new challenges, and new approaches are going to be needed for validating and testing this class of software. This is still very much an open problem in software engineering, and there also are creating new ways we develop and design software that could potentially be significant productivity boosters if they are used and applied correctly. Now that we know a little bit about the nature of software, an important question to ask is, how do we make good software? Or perhaps, what even is good software? This could be somewhat subjective, but from a software engineering standpoint, good software is software that meets the requirements of our customers, end users, and anyone who holds a stake in the success of a software project. This can be ensuring it functions without error or defect and does what we want, but can also include other aspects such as usability, maintainability, and performance. It can also be about the process itself. Was it completed within budget, and was it made on time? So how do we ensure our software is good? And the answer is by applying a systematic, disciplined, and quantifiable approach to its development. That is, by applying software engineering principles to the discipline. Software engineering can be seen as a layered technology, with each layer depending on the one under it. At the foundation is a commitment to quality. Without a commitment to quality and a culture of continuous improvement, no organization or team can hope to create good software. Time and resources must be committed to ensuring the quality of software created, or the effort is effectively compromised from the start, and you'll spend the project reacting to defects instead of delivering value to your customer. One layer up is process. Process defines a framework for the effective and timely delivery of software. These processes guide the technical methods applied, the work products produce, ensures quality, and helps manage change. In our next video, we'll be exploring process and the process framework in far more depth. Next are methods. Methods provide the technical how-tos and the best practices for building software. They encompass a broad range of tasks, including how we communicate with stakeholders, analyze requirements, and design and construct our software, as well as how we test and support it. At the top are tools. These support and automate the software engineering process. They help us manage change, create and share documentation, and test our software and track issues. Some examples include source and version control, such as Git and SVN, frameworks for creating unit tests, such as JUnit, tools for generating documentation from comments like Javadoc, and management software for tracking the progress of a project, and tasks to be completed and any issues that arise. So some examples would be things like Jira or GitLab. So that's all I have for you in this video. In our next lecture video, we'll explore the software process in the process framework. That was that second layer of the software engineering stack that we just saw. Thank you for watching, and have a great day.